We're just going to jump into big idea number 5. This is all thermochem. So thermochem, thermodynamics, basically everything that has to do with energy. That's big idea number 5. And as you're working through these multiple choice questions, if you notice at the very bottom, because you know it says like chapter 6, chapter 7, that doesn't actually correspond to the big idea. So if you actually look at the very bottom, it actually says like big idea number 5, thermodynamics, something about thermodynamics. Just so you have an idea. Okay. So there's a lot of information on every slide. I'm going to kind of point out the important information. In terms of bond energy, bond lengths, and then the strengths of bonds. The bond strength, so like how strong a bond is usually determined by the distance between the atoms. So triple bonds are the strongest, single bonds are the weakest. A lot of times you see something that says bond order. Now, for, let's say, nitrogen, okay, N2 is N triple bonded to N. There's only one way to write this, and it's like this. The bond order is just how many bonds there are. So in this case, has a bond order of 3. However, in resonance, I know some people were asking about bond order in a resonance structure. And when you're looking at bond order in a resonance structure, what you do is you take the total number of bonds, divided by the number of bond groups. And I'll kind of show you what I mean by this. Let's see, what's a common resonance? Ozone, O3. Okay, so it's, don't forget the lone pairs. So it's oxygen in the middle, one is double bonded, one is single bonded. If you wanted to determine the bond order of this, you take the total number of bonds. Okay, count every line. How many lines are there here? 3. Okay, divided by the number of bond groups. So an area where there are bonds. How many areas are there where there are bonds? 2. There's one with the double, one with the single. What's 3 divided by 2? 1.5. That's the bond order for ozone. Okay, that's looking at bond order with resonance. And I know there was I think it was a multiple choice question. It may have been on one of the big ideas that we looked at last week. But bond order is just looking, if it's not just a single bond, if it's resonance, you have to take the total number of bonds divided by the bond groups. The higher the bond order, the stronger the bond. That's why triple bonds have a bond order of 3. That's as high as you can go, is 3. You have a quadruple bond. So bond order of 3 is going to be the strongest. Bond order of 1 is going to be the weakest. And then you can see multiple bonds shorten the distance. Bond energy is endothermic. A bond energy is the energy you need to break a bond. Think about breaking a stick. Right? Think about each one of these lines that we drew as breaking a stick in half. Right? You have to put energy in. So bond energy is endothermic. And then there are 3 factors that affect the strength of a bond. You can look at size. Okay, so as you look at size, think about like the nuclei. The closer they are together, the stronger the bond. The farther they are apart, the weaker the bond. You can look at polarity. Okay, because polarity is going to be really easier to break because if one atom is much more electronegative, it's pulling all the electrons toward it, kind of like when we talked about acids. And then bond order. Okay, the higher the bond order, the stronger the bond. And this just kind of shows you bond energy. Okay, the higher the number, like the C triple bond N, has a bond energy of 887 kilojoules per mole. So you have to put in a whole lot of energy in order to break that bond. This picture, if you were in class today and you did the multiple choice questions, there was something that looked kind of like this. It's potential energy, and then this curve represents distance between the nuclei. The most stable place is at the very lowest potential energy. Lowest potential energy is going to be the most stable. You don't want a whole lot of potential energy because that makes everything very unstable. Think about, like, you know, if you bring two magnets just close enough that you can start to feel them pulling on each other or repelling, that's a lot of potential energy. The most stable is when they're either really, really, really far apart or really, really, really close together. And in the case of atoms, you want them really close together. Okay, Maxwell-Boltzmann distributions. This usually comes in with gases, but in terms of the learning objectives, this fell into energy because it has to do with kinetic energy. What's the definition of temperature? Average kinetic energy. So if you're at a constant temperature, are you changing the average kinetic energy? No, don't let that trick you. Okay, temperature is average kinetic energy. Unless you're changing temperature, you're not changing average kinetic energy. Gas molecules that have larger mass will have a slower speed, a slower velocity, but if they are at the same temperature as a really light gas molecule, they have the same average kinetic energy. Right? Temperature is average kinetic energy. And then the Maxwell-Boltzmann distribution just shows you the number of molecules that exist at a certain energy. Okay, the higher the temperature, I don't care, grade book. My grades never go in right. So the higher the temperature, okay, the more particles you have at a higher average kinetic energy. The lower the temperature, the slower your particles are. So notice this is at a lower temperature. You have a smaller kinetic energy versus a high temperature. You have a larger average kinetic energy. Okay, and then when you increase temperature, you increase average kinetic energy. Oh, and then activation energy. You only change activation energy with a catalyst. That's it. Activation energy is never changed unless you have a catalyst. Okay, so some vocabulary that goes along with thermodynamics and thermochem. Universe. Universe is everything. Every single thing. This table, this chair, you, your pencil, my shoe, all the universe. The system is what we look at. Everything else is the surroundings. So you always have your system, you always have your surroundings. Endothermic, into. Endo is into the system. Exo, it exits the system. Think about exothermic and endothermic in terms of the system every time. Okay, so exo and endo, think about it in terms of only the system. It's going to be easier for you. Heat transfer. So as you think about heat transfer, one thing you want to know, heat flow goes from higher energy to lower energy. Right? So that's like higher temperature to lower temperature. That's why if you put an ice cube into a glass of pop, right, whatever pop you want to drink, right, it doesn't get, well, it's colder right away as your ice cube melts, and then it's going to warm back up. And that's because the energy from the pop is actually going into the ice cube to warm it up, or you can think about the other way. But they come to thermal equilibrium, and then that is cold, but everything else, the surroundings, is warmer, and so the surroundings will actually transfer heat to the pop, makes it warm up again. Right? Everything pretty much always goes warm eventually. When they are at equal temperatures, they are at thermal equilibrium. Right? They've balanced each other out. Specific heat, no water specific heat. What's water specific heat? 4.184 joules per gram degree Celsius or gram degree Kelvin. It's the same thing because delta T is going to be the same. You can measure heat transfer in terms of Q equals MC delta T. And conservation of energy. Energy is conserved, like mass. Can't get rid of it. You might think, well, I can lose energy. Well, it still goes into the surroundings. It doesn't just disappear. Temperature, again, measure of average kinetic energy. Don't forget that. Don't let that be the multiple choice question that you miss. Energy can be transferred either as work or as heat. You can think of work one of two ways. If it's a gas, you can think about it as pressure times volume. If it's really anything else, if you take physics, you're going to learn work first as force over a distance. So like if I push this table, I'm doing work on it because I'm exerting a force over a certain distance. Really, you just need to know that work is one way energy can be transferred. We don't really do a lot with work. We normally just focus on heat because everything that we do assumes this pressure is constant, and that gets rid of our work. Right? And then our energy and our heat are what we look at. Okay? The only time that we look at work is when we're dealing with a gas. Right? If you expand a gas, so if this is what we start with initially, and then the volume increases, it expands, the gas is doing work. Right? It's pushing this up. That's the gas doing work. If this gets pushed down, that means that your surroundings is doing work on the gas. So it just goes back to you always have your energy going somewhere. Either your system or your surroundings. You can never lose it. Okay, this is something that people normally, this is like the one thing with Q equals MC delta T that people usually get tripped up on, is thinking about solutions. Because when you think about solutions, you guys normally think about the water being part of the solid. And when you think of solutions, the water is your surroundings. Right? You start with a solid, you dissolve a solid, and the water is your surroundings. So like ammonium chloride. Okay, when you put ammonium chloride in, your temperature goes down. Okay, what are you measuring the temperature of when you stick the thermometer into the calorimeter? The water. Okay, that's your surroundings. So when you put it in and the temperature goes down, the solid is your system, which means it's endothermic. Yeah. Okay. Or when you guys put in calcium chloride, that's what a lot of you guys picked for the hand warmer that you made. You stuck the thermometer into the calorimeter and your temperature increased. Okay, that's because the water is your surroundings. You measure the temperature of your surroundings.
So when we did the lab and we added KOH to the acid and it got really hot, we had to put in ice bath. Was that an exothermic?
Exothermic.
That was exothermic,
Yep.
right?
Yep. Because you always want to think like what you feel, you're the surroundings.
That's what I thought. Somehow I got what you said. That was endothermic. I don't know why.
So here's what you can think about. Think about like putting your hand on the beaker. Well, you didn't want to because it was so hot. But either way, you put your hand on a beaker and you feel it hot. Right? Energy is being released to your hand. Your hand is the surroundings. That's exothermic. If it's cold, right, so when you guys did the ammonium chloride, if you put your hand on like the coffee cup or on a beaker and it feels cold, it's absorbing energy from your hand. That's endothermic. So you can kind of think about it like that. Like if I put my hand on it, what would I feel? And your hand is the surroundings. And then in terms of Q, this is always a big one that a lot of people forget. Your energy that's lost by the system, this is assuming it's exothermic, lost by the system is gained by the surroundings. Or it could be the other way around. If it's endothermic, this will be positive, this will be negative. It doesn't really matter because it's essentially the same thing as this last bullet point. Q1 plus Q2 equals 0 because energy is always conserved. So if you have like a solid plus the water, Q of the solid plus Q of the water equals 0. So even if you're not sure which is exo and endo, you can do it this way. It's always going to add up to equal 0. And that's going to help you determine your heat. And we talked about calorimetry when we looked at labs, but you always use the coffee cup. It's usually what you use. You can use it to solve for heat capacity, specific heat. Maybe you want to find delta H of a reaction. And then this goes back to what we just said. Everything, all of your heats add up to equal 0. And so you guys essentially did the opposite, positive Q equals negative Q. This has a lot of variables on it, but essentially the same. It all comes back to Q plus Q equals 0. If you have to find the calorimeter constant, that's just when you do C times delta T. I don't see them making you find the calorimeter constant, just because that's just an extra step, and you probably won't have time. I would see, if anything, you would just be doing Q equals MC delta T. On the multiple choice questions today, you guys had at least, it was like a set of questions that dealt with Q equals MC delta T. And then delta H of reaction. Just keep in mind the major difference between Q and delta H. Q is going to be just joules or kilojoules. Delta H is joules or kilojoules per mole. So Q, you're not going to have the per mole. Delta H, you're going to end up taking your Q and dividing it by the number of moles, probably of solid that you dissolved, to get your delta H. And that's what you did with the hand warmer lab. You had to actually divide. And then heating and cooling curves. Whether it's a heating curve, whether it's a cooling curve, two things to keep in mind. If it is an incline, okay, if it has a slope, you're using Q equals MC delta T. If it's a plateau, you are just using Q equals M times delta H. Okay, because delta H is going to be your phase change. So if it's solid to liquid, okay, it's going to be your melting. Okay, so that's going to give you your solid to liquid. It's going to be your heat of fusion. Okay, if it's going liquid to gas, that's your delta H vaporization. They'll have to give you those. They're not going to make you memorize those. I think we made you memorize them last year, but you don't have to know them this year. They'll give them to you. They'll say, you know, heat of fusion of water is this. Heat of vaporization of water is this. And then if you wanted to go all the way from here to here, you're going to do Q equals MC delta T, Q equals M delta H, plus Q equals MC delta T, plus Q equals M delta H, plus Q equals MC delta T. So you're going to be doing what? 1, 2, 3, 4, 5. You'll be doing 5 calculations and adding them all together. If they did that, it would have to be in a free response, unless they made it really easy math for you again. And then, you know, the other way going down. So just remember, if you have temperature changing, you're using Q equals MC delta T. If it's a plateau, okay, phase changes, you're at equilibrium, and you're just using Q equals the mass times delta H of the phase change. So here's a question. You guys will be able to work with your groups. This is a multiple choice. Don't ask lab-based multiple choice questions where no math is involved, but you're basically analyzing. So a student's using a calorimeter made from a styrofoam cup and a thermometer to determine the specific heat capacity of a solid. The cup was weighed, filled with 100 milliliters of water. Just a quick check. What's the density of water? 1. Make sure you know that, because it'll tell you, like on the multiple choice today, assume the density of water. I mean, just don't forget little things like that. So after the water reached equilibrium with the room temperature, temperature was measured at 25 degrees Celsius. Piece of metal was found to weigh 50 grams. Solid was heated to 100. After the solid was placed in the water, it reached a maximum of 40. During the experiment, the student failed to put a top on the cup. How would this have affected the calculated value for the specific heat of the unknown solid? So essentially it's asking you what you calculate for specific heat. What happened because you forgot to put the top on, which I think some people actually did that in the lab. So talk to the people next to you and see if you can come up with an answer. Okay, so for people that were talking, correct answer is going to be B. Okay, the value is going to be too small. I heard some people say heat's going to be lost to the surroundings. Okay, so your heat is not going to be as high as it should be. So as the temperature of the water increases, energy is going to be lost. Okay, so you're not keeping all of that heat in. And so you're going to get a lower value of specific heat. Your delta T isn't going to be, it should be a lot bigger. So that's going to give you then a specific heat too small. Okay, again, there's lots of information on this slide. Here's the big thing that this is saying up here. I'm going to summarize this for you. This is saying if you want to find delta H of a reaction, and you're dealing with bonds, bonds broken minus bonds formed. That is what that is telling you. All right, so we have the delta H of reaction equals the sum bonds broken minus the sum of bonds formed. This is something that is not on the equation sheet, but you want to know. Okay, broken minus formed. And here's why it's like this. Because bonds breaking, that's endothermic. All of these values are going to be positive. Okay. Bonds forming is exothermic. When you bring two things together, that releases heat. Those are exothermic. This negative distributes to every one of these values to make each one of them negative. That's why we do broken minus formed. And so, depending on how many bonds you're breaking and how many bonds you're forming is really what determines the overall process. If you're breaking more bonds than you're forming, you're putting in more energy. You're exerting yourself too much, and it's still going to be endothermic. If you're breaking like one bond and then you're forming, 5, you're going to get a lot of energy out of that. But if you need to calculate that, draw the Lewis structures if they don't give it to you. Then it says don't forget double and triple bonds. What's the shortcut that you can use for double and triple bonds? 6n plus 2 rule. Right? You have 6n plus 2. What are the atoms that could double or triple bond? Okay, cons. And then when you do 6n plus 2, there's one atom you exclude. Hydrogen. Alright, so that's how, if you wanted to know what kind of bond forms between N2, you do 6n plus 2. N is the number of atoms. So 6 times 2, N's. 6 times 2. Okay, I am tired, okay. 6 times 2 plus 2 is 14. Compare that to the valence electrons. How many valence electrons does one N have? 5. So 2 N's has 10. Compare 10 to 14. That's 4 less. That means you either have 1 triple or 2 doubles. Well, we don't have a place for 2 doubles, so it's going to be a triple bond. So don't forget about that 6n plus 2 rule. And then you just look at broken minus formed for your delta H. And then that's kind of just comparing to these reaction diagrams. Right? If you're releasing energy and it asks you a question about bonds broken minus formed, if it's exothermic, that means that you've probably formed stronger bonds, you've broken weaker bonds, so you're releasing energy. If it's endothermic, that means you're probably breaking stronger bonds, and you're forming weaker ones. Now keep in mind, when we talk about bond energy, you're actually breaking bonds. You're breaking covalent bonds, not intermolecular forces. You're actually breaking bonds within a molecule, not between. And then electrostatic forces. Electrostatic forces, we can talk about intermolecular forces or even ionic attraction. With intermolecular forces, Okay, the stronger the intermolecular force, the more energy it takes to break, the higher the boiling point and or melting point, and the lower the vapor pressure. This was a question on the multiple choice on the practice today, and a lot of people flipped it. Okay, if it says greatest to lowest vapor pressure, great vapor pressure means that you have very strong intermolecular forces in the liquid. You're not going to have as much pressure above, because remember, vapor pressure is just the pressure above a liquid. So if it's a low vapor pressure, you don't have very much gas, so the liquid molecules are still pretty attracted to each other. If you have a high vapor pressure, a high vapor pressure means that the liquid, it was easy to break the bonds between molecules and you have a lot of gas. So the higher the vapor pressure, the weaker the IMFs. And so as you go through intermolecular forces, okay, dispersion is going to be the weakest, so those have the low boiling point, high vapor pressure, relatively easy to break. Okay, and remember, these are between molecules. Then you have dipole-dipole. Well, you have dipole-induced dipole. This is if you have a polar molecule and a nonpolar molecule coming together. Polar molecules, well, I need to stop saying like they actually talk because, you know. But if one of the chlorines comes close to one of the chlorines within the Cl2, the electrons are actually going to repel all of the electrons on the Cl within HCl. And it's going to actually create what's called an induced dipole. That's dipole-induced dipole. I don't think it's going to talk as much about dipole-induced dipole as just the dipole-dipole. So that's just between two polar molecules. And then hydrogen bonding, HNOF, right? HNOF. It is between two molecules, not within. Okay. This bond in water, okay, the bond between an O and an H within a water molecule, that is not a hydrogen bond. What kind of bond is this? It's a covalent bond. It's within a molecule. You have covalent bonds within a molecule. Now, if I brought another water molecule near this, the attraction is the hydrogen bond. Which of these do you break when you boil water? The hydrogen bond. You do not break a covalent bond when you boil water. And so normally they're going to ask you questions like this within free response when you're justifying, or maybe even multiple choice.
So if there was like a polar molecule that didn't have like H on it, and there was hydrogen there, could it?
It would dipole-dipole.
But could it form a hydrogen bond with water or another compound?
Like, what do you mean? Like, think of a molecule that you're saying, like HCl. Let's look at HCl. Okay, because in order to hydrogen bond, you have to have a hydrogen attached to NO or F, and then you're bringing the two molecules together. So if we had HCl coming near a water, this H, you would have this attraction right here, but this is not a hydrogen bond. It's dipole-dipole. Yeah. So in order for this to be a hydrogen bond, this has to be NO or F. And then also, you know, obviously the O has to be NO or F. Yeah. Yeah, so if both molecules do not hydrogen bond, it would just be dipole-dipole. Or if, you know, instead of HCl, if that were CH4, then the strongest between the two would be dispersion. Yeah. Okay, and another thing to look at is inter versus intra. And I never thought about this until I saw this picture, right? Like interstates, right, are like highways. Right? Interstates are between states.
Oh, how about that?
Yeah, like inter. So like I actually like didn't even think about it. So like intermolecular forces are between molecules. Okay? Intra would be like an ionic or a covalent bond. And so a physical change involves intermolecular forces. When you boil water, you are breaking hydrogen bonds, not covalent bonds. You would have to run electricity through water to break the covalent bonds. That's a chemical change. You're changing water. Okay, so chemical change, that's when you're looking at intramolecular covalent bonds. Okay, intermolecular forces are going to be much weaker, easier to break. So this shows you the different types. You go from the weakest intermolecular to the strongest intramolecular. So we go from dispersion, dipole-dipole, hydrogen bonding, and we have covalent bonds, and you don't even have the ionic up here, but ionic is going to be the strongest. Okay, and then if you're asked to rank molecules in order of whether it's melting point, boiling point, viscosity, vapor pressure, they just want you to look at IMFs. Okay, if you are asked to look at a physical property and they give you Lewis structures, you're looking at intermolecular forces. First, look for molecules that could hydrogen bond. So that's going to be the strongest. Then look for dipole-dipole. That's going to be the next strongest. And then look for dispersion. With dispersion, the stronger dispersion forces are the ones with more electrons, not greater mass. Now you're like, well, but those are the same. You're right, they are the same. But when you're explaining, if you're explaining a free response question, you have to explain stronger dispersion forces based on more electrons because it becomes more polarizable, making stronger dispersion forces. Okay? So the larger molecule is going to be the stronger dispersion force. And then so like a tiny CH4, so it's going to be weak dispersion compared to like C100H, 200. That's going to have stronger dispersion forces because it has way more electrons.
Wait, so when it becomes more polar, that's like the intermolecular forces are stronger, but the intra, would that be weaker? Like if it was a polar.
So are you talking about just more polarizable? Or what are you, covalent's always going to be stronger than any intermolecular force.
Okay.
So when you're comparing like melting point, boiling point, vapor pressure, you're only looking at inter. So you're looking at hydrogen bonding, dipole-dipole, or dispersion. But I'm talking like if you are asked to rank, okay, these are all H's. So C2H6 compared to CH4. And you have a question that says, which has the higher melting point, or higher boiling point? So first think, what does it mean in terms of intermolecular forces if you want a higher boiling point?
Stronger.
You want stronger. Okay, so first thing we want is stronger IMFs. Okay, so now let's look at each of these and see what's the strongest type of intermolecular force that it could have. Right, so what's the strongest IMF that this could have? Dispersion. Because they're all CH bonds, and every CH bond is nonpolar. So the strongest we could have in C2H6 is dispersion. What's the strongest we can have in CH4? Dispersion. Okay, so they both can only interact using dispersion, but we can compare the strength based on the number of electrons. So which has more electrons? The top one. C2H6 has more electrons, so these dispersion forces are going to be stronger than CH4, so C2H6 is going to have the higher boiling point compared to CH4. That's going to be what you're going to look at. And I think there was one in the multiple choice, at least one, there may have been more than one, where they gave you organic. You guys are like, do we have to know organic for the AP test? No, because every organic molecule that they give you, they're going to give you the Lewis structure, so you can actually see if it hydrogen bonds or if it has dipole-dipole. One thing I will show you is if you have something that is C double bonded to O, and then the C has maybe two H's coming off of it. Does this hydrogen bond? No. In order to hydrogen bond, the O needs to be attached to the H. It's not. So what type of intermolecular force will this have? So it will have dispersion, but then it also has this negative up here. So it will dipole-dipole. Now, why did I say it does have dispersion? Everything has dispersion, right? Everything has dispersion. And the reason that this is dipole-dipole is because you don't have this negative anywhere else. It's only on this side, which leaves this side partially positive. Okay, intermolecular forces in biological molecules, they added this in this year. They just want you to see, like, DNA hydrogen bonds. They had a question 2 years ago where they gave you DNA and they said, which of these are hydrogen bonds? And you picked the one that was O attracted to an H or N attracted to an H with an H bonded to it. That's the only thing that they're getting into this year. Like, they don't really care if you know about DNA or if you know about enzymes. All they want you to know is hydrogen bonds can exist anywhere. Okay, then entropy. Embrace the chaos. Should be like this slogan. AP Chemistry, embrace the chaos. So entropy, you can think about it as chaos or as disorder or whatever word you want to remember, but it's delta S. These are ways you can increase delta S. And Noah's not even here for me to say you increase volume. Okay, because when you increase volume, you increase the space that your gas molecules can be chaotic. So the more space they have to be chaotic, the more chaotic they're going to be. So you can increase moles, you can increase temperature, you can increase volume. You can go from a solid to a liquid or from a liquid to a gas. And then you can form more complicated molecules because you have more electrons. More electrons, more chaos. And so, again, particle diagrams. Maybe you have a question that says, which of these has the highest entropy? Okay, it's going to be the gas that has the most disorder. And then predicting how reactions will go. When you are predicting favorability, that's the word that they use now. Thermodynamic favorability. They don't use the word spontaneous anymore. They say which is more favorable. That means which is more spontaneous. You always look at delta G. Okay, if delta G is negative, it's always spontaneous. Well, if delta G is negative, it will be spontaneous. Then you have these situations. Know this chart because they will ask questions on it somehow, some way. If delta H is negative and delta S is positive, that's nature's ideal scenario. Right? Low energy, high chaos, right? High disorder. That's what nature wants. Spontaneous all the time. If it's endothermic and lots of order, that's opposite of what nature wants. That's never, ever spontaneous, no matter what temp you're at. And then if delta H is negative, if they're the same sign, right? So if they're both negative, it's spontaneous at low temperatures. If they're both positive, it's spontaneous at high temperatures. There's a question on one of the multiple choice questions I saw said, at these conditions, when will the reaction be spontaneous? And it was like, actually, I think it was one of the multiple choice questions in this when I was copying it. And it gave you delta H, and then you had the reaction, so you could see if delta S would be positive or negative, and then you just had to answer the question. A way to find delta G, to bring everything together. Delta G equals delta H minus T delta S. Caution. Most missed right here. Delta S is given in joules. Watch your units all the time. Take your time and watch your units. I need to go to bed. Entropy is in joules. Okay? If entropy is in joules, you need to convert it to kilojoules. Okay? Your units have to be the same. And then, you know, using this right here, you can figure out really anything. When you're undergoing a phase change, whether it's solid to liquid, liquid to gas, whatever it is, what is delta G? What's delta G when you're undergoing a phase change? 0, because you're at equilibrium. Delta G is 0 at equilibrium. And so then if it says, you know, here's the temperature at which you go from solid to liquid, what is the delta H if this is your delta S? So they could ask you a variety of things. So how can you calculate delta G? Well, you have formation, okay, products minus reactants. They'd have to give you these values. This is on your equation sheet. This is on your equation sheet. And then delta G equals negative NFE naught. That's also on your equation sheet. And so is negative RTLNK. Right here. Right, these are all in your equation sheet. You just need to know how to use them. So negative NFE naught, this is going to be for galvanic cells. Remember, they use the term galvanic, not voltaic. Negative RTLNK, that gets you between favorability and equilibrium constant. And then the other two just get you delta G, depending on what you're given. This top box, this is useful because it shows favorability, so whether something is spontaneous, it shows you your cell potential, and it shows you equilibrium constants. Bless you. So when delta G is negative, your reaction is going to be spontaneous. That's what delta G tells us. Well, if delta G is less than 0, your K is going to be greater than 1, because your products are favored. But your cell potential will also be greater than 0. Because remember, when your cell potential is greater than 0, it's spontaneous. Okay? And then it's going to be just the opposite if it's not spontaneous. And if you're at equilibrium, delta G is 0, E naught is 0, and K is 1. Because your cell doesn't work if it's at equilibrium. You have no potential. So there are a lot of different ways that you can calculate delta G. This E naught of cell, you no longer have to know. That's the Nernst equation. You just have to know if it is at equilibrium, it's 0. Further away from equilibrium you are, the higher the cell potential. The closer to equilibrium you get, the closer to 0 your cell potential gets. Okay, and now they're throwing in coupling reactions. It sounds very complicated. The only thing that coupling reactions mean is that if one reaction is not spontaneous, but you want it to go, you just couple it with a very spontaneous reaction, and it's going to push the other reaction to start. Okay, that's what a coupling reaction is. And I'm going to show you. It's talking about Robin Hood. Okay, here we go. So reactions can be coupled together. Typically, it's when they share an intermediate. So A plus B is at equilibrium with C plus D. So this A plus B, we're going to assume it's not spontaneous. Right? It doesn't want to go on its own. But some of it will. You always have a little bit that'll go. Well, if you couple it with this reaction, which is very, very, very spontaneous, as soon as you make some of this D, it's immediately used up. That's going to keep this reaction going. Even if it just goes a little bit at a time, it's going to keep it going because you're using it up right away. That's a coupling reaction. That's used all the time as chemists start to actually kind of create their own, like as they're synthesizing like new medications. They use coupling reactions a lot because the whole point of coupling reactions is to increase favorability. You just want to increase a spontaneous reaction. You want to make it more and more spontaneous. Okay, so then, again, the way that K works, right, is as you have an intermediate, it's like Hess's law. It's just another way to say Hess's law. As we have one reaction going, the other one's going to go, we get two delta G's or delta H's. When you're dealing with delta G's and delta H's, you add them. When you deal with K's, you do not add, because K's are exponential, and you multiply, and you go to the 1/2 power or to the 2nd power. So if you have, this is technically considered a coupled reaction. It's a two-step mechanism. You guys know coupled reactions better as reaction mechanisms with elementary steps. That's what these are. We just haven't called them coupled reactions. If you want to find the overall K, you multiply them. Right? If you want to find the overall delta H, you add them. Hess's law is dealing with coupled reactions. They just want to throw in new terms. That's all they want to do. You guys have done all of this before already. Okay, so again, like I said before, this is just coming back to if it's not spontaneous, your reactants are favored. That could be whether it's delta G or K. If it's less than 0 and K is greater than 1, products are favored. Right? Just think back to if it's K, what do you have more of? It's products over reactants. So think about, based on the sign of K, do you have more reactants or more products? In terms of vocabulary, if it talks about whether something is favorable, you're looking at delta G. Let's see, what were other terms that we had with delta G? I tried to write all of them out. If you're looking at, if it specifically says are products or reactants favored at equilibrium, you're probably going to be dealing with KEQ, equilibrium constant. If it talks about how fast a reaction is, you're dealing with kinetics. So it's just looking for small words. Favorable means spontaneous. That's going to be the one thing. If it talks about being thermodynamically favorable, it's looking at whether it's spontaneous or not. What's favored at equilibrium? Probably going to be looking at K. And then how fast something is going to be kinetics. Okay, we've already looked at delta G and RTL and K. And then this just shows you, okay, when delta G is really big. Okay, this is positive. So what does it mean if delta G is positive? It's not spontaneous. And when it's really positive, it's really not spontaneous. Your K is 10 times 10 to the negative 36. That's very reactant favored. Right? So this says you essentially have no forward reaction, and your reverse reaction will be spontaneous. Right? If your forward reaction is not spontaneous, then your reverse reaction probably is. Where if you're the opposite and delta G is very, very negative, it's very spontaneous, K is very big, basically you have your forward reaction going to completion. You have basically all products at equilibrium and really no reverse. If delta G is 0 and K is 1, those are your equilibrium conditions.